Hello ladies and gentlemen, we're going to do some 1-2 review. So this is the study guide. This is everything that we've done so far in section 1-2. First thing we're going to talk about identifying local mins and maxes, intervals, and boundedness. So we've got our function here. We're going to use Desmos to graph it. So let's see, I think I got this thing already typed in. There you go. Negative 3x to the fifth minus 2x to the fourth. Yeah, that looks right. Okay. So here's my polynomial. And what I'm going to do is, just to make this easier to talk about, I'm going to click these points and screenshot this thing so I can not have to keep flipping between them. So I've got my graph, and I'm asked to analyze a bunch of stuff about it. So let's see if I can do this in a way that is useful. First thing, it says, what are the local mins? So you can see here in my graph, the local mins are going to be, there's only one of them. It's a turnaround point, and it's at the bottom. So a minimum is, imagine if I just took all this stuff out of it. A minimum in an interval is called a local minimum. So it's like, that's the smallest point. That's a turnaround point in that interval. So when it says local min, the only local min in this problem is going to be at negative 0.31 and then negative 0.459. That's an ordered pair. The local max is up here, so same idea, it's a turnaround point, but that one's going to be 0.82 and 3.806. So I have my local mins, I have my local maxes. Now the turnaround points are what I'm going to use when I talk about intervals. I don't really care about these zeros or the y-intercept or any of that other stuff. All I care about are the turnaround points. So all of my intervals are going to use these x values and then two positive or negative infinity, basically. So let's write these in interval notation as increasing, decreasing intervals. So the increasing intervals are the ones where it's going up as we read left to right, so that's from there to there. And you use the x values only. There's no y values in intervals. So the x values are negative 0.31 to 0.82, and we use brackets to say the endpoints of intervals. So negative 0.31 to 0.82, that's our interval of increasing. Now I need to do my interval of, oh wait, I copied that wrong. That's the increasing. How do I just move that over? Who does decreasing first? There we go. There's increasing. So that's my interval of increasing. Now I'll do interval of decreasing. Decreasing is from there and there. Those are going down as you read left to right. So this thing goes to the left forever. It's not that it's going up. We're talking about x values. It's going left. So it's going left, negative infinity, and you can't get to infinity, so it's parentheses. To this x value is negative 0.31, and we say bracket, union. That's the first interval. Then this interval is from 0.82 to, again, we're going to the right. It doesn't matter that it's going down. It's going to the right. We know it's an interval of decreasing. We know it's going down. X is going right, so x is going to positive infinity. So 0.82 to infinity. So interval of decreasing right here, and interval of increasing is the only one in the middle. You can tell that there's three intervals because there's two turnaround points. Then the last thing is this function bounded. So if you look at it, it looks like it goes up forever and it goes down forever. That means it is unbounded. It goes up, that means it's not bounded above. It goes down, it's not bounded below. So we say it's unbounded. Let's try another one. I'll do the same thing here. I got my graph, so that's this guy. Let me zoom in a little bit, see if I can maybe see this better. That looks pretty good. Okay. So that's all I really care about. Let me look at my picture. Alright, so we're going to first talk about local mins and local maxes. Local mins are the turnaround points at the bottom, so this guy and this guy, those are local minimums. So that would be negative 0.366, negative 0.25, and these are ordered pairs, so they're in parentheses, and 1.366, negative 0.25. Those are my local mins and maxes. Now for my intervals, remember, we're using only these x values. If you use any of the y values, I know you don't know what you're doing. So interval of decreasing, and I'll do it right this time, in the right order anyway. Interval of decreasing is there it's going down as you read left to right, and there it's going down as you read left to right. So to say that in interval notation, we say negative infinity to negative 0.366, bracket, union. This interval is 0.5 to 1.366, also brackets. Interval of increasing. So for increasing, we do the same thing, but we're talking about these intervals, because that's where it's going up. So that would be negative 0.366 to 0.5 in brackets, and then union 1.366 to, as x goes to positive infinity, we're increasing. Okay? Those are intervals of increasing, and you'll notice that this thing has a bottom. It has an absolute minimum, a global minimum, I guess you could say. You say it's a minimum. That means it is bounded below. It doesn't go below a certain point. The smallest y value is negative 0.25, and it doesn't ever go below that. So we say it is bounded below. It's got a boundary on the bottom. It's bounded below. We've got one more of these guys. So negative 2x to the fourth, that looks like this graph. Okay, I gotta zoom that thing out. Let's see, zoom out a little bit. Come on now. Oh, okay, just opens down. So this one's kind of funky looking. Cool. Stretch out a little bit. All right, there's my turnaround point. There's only one turnaround point in this graph. So local mins, in this problem, there are none. So we'll just say there are no local minimums. It doesn't turn around that way. But there is a local max, 1.385, 6.151. Intervals of decreasing. So you can tell there's only one turnaround. That means there's only going to be two intervals. Interval of decreasing is 1.385 to infinity. Interval of increasing is negative infinity to 1.385. And we say that this is bounded above because it has a boundary at the top. It doesn't go below a certain point, or it doesn't go above a certain point, rather. It has a maximum, and its maximum y value is 6.151. So this is bounded above. It's got a boundary on the top. So that's it for our intervals and local mins and maxes. Now let's talk about discontinuities. So this says state whether each function is continuous or find the discontinuities. So I'm going to do the same thing. I'm going to screenshot this guy. But before I even do that, you know what? Let me just analyze it before I see the picture. Sometimes it helps to kind of go in and not know what it's supposed to look like. So we have negative x plus 2, and I'm going to factor the denominator because the name of the game is figure out where the denominator is 0. Find the zeros of the denominator. If you factor the bottom, you're going to get x plus 5, x plus 2. And those factors cancel out. But before I even do that, I want to just observe that x cannot be negative 5 and x cannot be negative 2. The reason it can't be negative 5 is because if you plug negative 5 in, you will get 0, and then the denominator is 0, and then you're dividing by 0, and that's not going to work. Same thing with negative 2. Even though that factor cancels out, you can't plug negative 2 into the original function, which means it's not in the domain. So we have two discontinuities here. And what I'm going to do is say, I know what types of discontinuities they are. There is an infinite discontinuity at x equals negative 2, and there is a removable, watch this, so I don't have to keep typing this. Yep, at x equals negative 5. So what's that going to mean? There's an infinite discontinuity. Infinite discontinuity is a vertical asymptote at negative 2, and a removable discontinuity at negative 5. A removable discontinuity is a hole in the graph. You're not really going to see it unless you know to look for it. So let me look at the graph now and see if this stuff looks like what I think it should look like. And notice there's a little sneaky minus sign in there somewhere. So here's my graph. And I said that there was an infinite discontinuity at negative 2. So does that look like there's a vertical asymptote at negative 2? I could just even type x equals negative 2. Uh-oh. Did I type this in right? X plus 2, x squared plus 7, x plus 10. Oh, no, I said it backwards. The removable is at negative 2. Oh my gosh, I gotta fix this. Sorry, guys. So, the removable discontinuity is the one I crossed out. I removed the one at negative 2, so I typed them in backwards. The removable discontinuity is at negative 2. So let me look at the picture. Removable at negative 2. Wait, where's negative 2? Right there. Undefined. Yes. Good. Removable at negative 2. I wish I could screenshot that. And then the vertical asymptote is at negative 5. There we go. All right, we fixed it. So let's go ahead and screenshot that thing. So you would sketch the graph. It would look something like this. And I'm going to make sure that in my picture, the one that I crossed out, the discontinuity that I removed, is at negative 2. So I should be able to see on my graph at negative 2 an open circle. 2, 4, 6. Yeah, so these are counted by 2. So right there. You should have an open circle at negative 2 and then a vertical asymptote at negative 5. So once again, if you cross a factor out, you can think of it as removing the factor. That is a removable discontinuity, and that shows up as a hole in the graph. If the factor doesn't cancel out, like -5, then that is called an infinite discontinuity, and that's a vertical asymptote in the graph. Let's do another one. X minus 3 over x squared plus x plus 1. So I'm going to try and factor the denominator. What multiplies to 1 and adds to 1? 1 times 1 is the only thing that multiplies to 1, or -1 times -1. So I'm not going to be able to get 1 here. This isn't factorable. So what I'm going to do is say, well, maybe it has zeros, but I have to do the quadratic formula to find them. Before I kind of go down that road, let me just see if I should even bother. Let me graph just the denominator, and we're going to look for zeros. So I'm just going to graph x squared plus x plus 1, and then you're like, oh, I get it. If you look at the denominator doesn't have any zeros. If the denominator never hits the x-axis, it never has any zeros. If it never has any zeros, then it will never be 0. If the denominator is never 0, we don't need to worry about dividing by 0 because that can't happen. So what I'm going to do is look at the graph now, but I'm pretty sure since there's no issues in the denominator, it's going to be a continuous function. And there's the graph, and you can tell, oh yeah, it's continuous. It's one of those bounded functions. So here's my graph. And since there are no discontinuities, since the denominator is never 0, then we just say that this function is continuous. Okay? It's a continuous function. There are no discontinuities because the denominator is never 0. A couple more. I just factored this. It's the same thing. X plus 5 over x plus 5, x plus 2. This is a very similar problem, but you'll notice that here, I could have screenshotted that other thing I wrote. In this problem, the discontinuities are what I said they were in the other problem. So since the x plus 5 cancels out, there is a removable discontinuity at x equals -5. Strike 3. Okay. Removable discontinuity at x equals -5 because the factor cancels out. So we'll see a hole in the graph at -5, and there is an infinite discontinuity at x equals -2. So at -2, we should see a vertical asymptote, and at -5, we're going to see a hole in the graph. So let's see how our graph looks when I actually use Desmos. X plus 5, that's this guy. Okay, so what do we think? At -2, we have an infinite discontinuity. That looks like it could be -2. I can even say x equals -2. Yup, okay. And then at -5, we have a removal. Yep, there it is. So unless you know to look, you're probably not going to see that removable discontinuity. So there's our picture. I'm just going to screenshot it. And I will make sure that I will draw my discontinuities. So I have a vertical asymptote at -2. That's right here. And then I have a removable discontinuity at -5, so right there. And I make this asymptotes, you should make dashed lines. So there you go. Let's do one more. X squared minus 5x plus 4 over x minus 4. So here, I don't really need to factor the numerator as far as the zeros are concerned, but I might have a removable discontinuity. X minus 4, x minus 1 over x minus 4. So if you factor the top, x minus 4, x minus 1, and then you'll notice these cancel out. So all that's left is negative x minus 1, which is a line. You could simplify that negative x plus 1. So I think if I just tried to graph it, I'd start at the y-intercept and go down 1 over 1. This is going to be the graph. I could draw this one very easily. But since I crossed out that factor, x minus 4, that is a removable discontinuity. So there is a removable discontinuity at x equals 4. If you cross out the factor, that's a removable discontinuity. So on my graph, I need to make sure that at 4, 1, 2, 3, 4, I have an open circle. I'm going to try that again. Open circle. 1, 2, 3, 4. Like that. Make it real obvious that it's an open circle. You can't even see that. How about that? There you go. Okay, so at 4, I have an open circle, and it's the equation of a line, which I'm going to graph it in Desmos just to make sure, but I'm pretty sure if I cancel that factor out, I just left with x minus 1, and when you distribute the negative, you get negative x plus 1. So let's see how I did. All right, good. So the y-intercept is 1. goes down 1 over 1. And then at 4, we have our removable discontinuity. Come on, where is it? There we go. Removable discontinuity at 4. So I make sure that on my graph, I have a hole in the graph. So that's it for 1, 2 so far. If you're feeling good about that, make sure you get your My Math Labs done. And be sure to hit that like and subscribe button.